Alright, so let's take a look at the second type of proof in Pure 1, and that's proof by exhaustion. So proof by exhaustion just means, as you said, exhaust, right? It means just looking at every single possible scenario and proving that it's either incorrect or correct. Okay, so this one is very simple. You just have to look at every single example. So let's look at this one here. Prove that every odd integer between 2 and 26 is either a prime or a product of two primes. Right, so you just have to exhaust every single example. So for 2, well, that's just 2, right? The next odd integer is, so it's odd integers, right? So 3 would just be 3, 5 would be 5, 7 would be 7, 9 would be 3 times 3, 11 would be 11 times 1, 13 is 13 times 1, and just keep going until you just have to show each single scenario. Like this. 19 is 19 times 1, 21 is 3 times 7, and 23 is 23 times 1, 25 is 5 times 5. So as you can see, we're showing that they're all a product, or all the odd numbers are a product of a prime or a product of two primes together. Right, part B, or the second one, prove that the sum of two consecutive square numbers between 1 squared to 8 squared is an odd number. So squared numbers is like 1 squared or like 2 squared, right? So the two consecutive, if we sum them up, so the first one would be 1 squared plus 2 squared, 1 plus 4 is equal to 5, odd. And you just have to do this for every single example. 4 plus 9 is 13. 3 squared plus 4 squared, we have 9 plus 16 is 25. 4 squared plus 5 squared, we have 16 plus 25 is equal to 41. 5 squared plus 6 squared, 25 plus 36 is equal to 61. 6 squared plus 7 squared is 36, plus 49 is equal to 85, and 7 squared plus 8 squared, 49 plus 64, we have, what do we have here? 113. Okay, so as you can see, all these values are odd numbers, so we proved by exhaustion that they're all going to be odd numbers. And finally, prove that for all cube numbers, all cube numbers are either multiple of 9 or 1 more or 1 less than a multiple of 9. So this is slightly more difficult. So what we're going to say is, like before, we're going to say let n equal to 3k or n equal to 3k plus 1 or n equal to 3k minus 1, where k is all real numbers. That way we consider every single case, right? Because if k is 1, this first one will get 3, second one will get 4, third one will get 2. So we consider every single value or every single integer. And I said n cubed, right? So n cubed is equal to 3k cubed, which is 9k cubed. So this is a multiple of 9. For when n is 3k plus 1, so we have 3k plus 1 cubed. Just as a matter of expanding it, so we get 27k cubed plus 27k squared plus 9k plus 1, which I can take 9 out, right? I can factorize it by 9. So we're at 9. We're going to have 3k cubed plus 3k squared plus k, and leave the plus 1 outside. That way we've proven that this one here is a multiple of 9 plus 1, or 1 more than a multiple of 9. And n cubed, when it's 3k minus 1, same scenario, expanding it, 27 cubed minus 27k squared plus 9k minus 1. So this will be, once again, 9, 3k cubed minus 3k squared plus k minus 1. So you can see here, this one here is the multiple of 9. This one here is the 1 plus the multiple of 9, and this one here is 1 less than the multiple of 9. So we've exhausted every single scenario.